Today we're going to talk about the YOLOv4, optimal speed and accuracy of object detection. So this YOLOv4 paper is an engineering paper. It uses a lot of different works from the previous papers. So in this presentation, I cannot cover all of them since that would be a 3 to 4 hours presentation. So I will cover some of them. And I put all the important reference and papers inside the note sections of the Google Slides. So if you're interested, you can come always back to check the references. So let's get started with the agenda. We first talk about the object detector, architecture breakdown from the backbone, neck, and to the head. And then we will talk about the terminology of back of freebies and back of specials. Then we cover the architecture selections for the whole YOLOv4 and the selection from the back of freebies and back of specials. Then we're gonna show some final results and experiments that YOLOv4 do and to show why they claim YOLOv4 is the optimum for object detector. So start with the architecture breakdown. A common object detector is composed with few parts. The first, of course, from the input part, and then you have a backbone as a feature extractor. If you see the left-hand side, you have the image, the diagram covering from the different components. And if you see the right-hand side, there is some concrete example of the different component. So for the backbones, we have the VGG16, the ResNext, and EfficientNet baseline 0 to baseline 7. And in this paper, we will mainly focus more on the CSP ResNext 50 and also CSP Darknet53. And after the feature extraction from the backbones, you can pass through the things to the detector. But in between, there is some components called neck. The neck component is try to compose the informations from the different layers of the backbone to the detectors. So the common one is the feature pyramid network, FPN, or SPP, the special pyramid pool. Later we will cover some of them. And if you see the head, there is a difference between a one-stage detector and two-stage detector. For the one stage, the famous one is SSD and YOLO. And for the two-stage detectors, the represent one is RCN and family. So basically the difference between them is the two-stage detector need a regional proposal to tell where is the possible regions that contains the objects. But for the one-stage detector, is just the end-to-end from the backbone instructions, feature instructions to the end detection. So first, we're gonna talk about the back of freebies. The definition of back of freebie is the method that only change the training strategy or only increase the training cost. There's nothing to do with the inference. And in this diagram below, I'm gonna first tell you about how to read that. The round shape is just a different categories, and the rectangle box are the concrete techniques that belongs to those categories. So if we think about what is the method that only change the training strategy, but there is nothing to do with inference, the thing we commonly use is the data augmentation. So if you see the data augmentation categories go down with that would be the single image or multiple image. Let's have a look first with the single image. You can categorize them between the also into different categories like photometry distortion or geometric distortion. You can change the image properties of the photometry like brightness or the saturations. And for the geometric distortions, you can have cropping or flipping rotation. And there's also very common to have batch normalizations that fall into the category of normalizations of the network activations by the means and variance. And of course, if you have a different GPUs, you can have the cross GPU batch normalization approach. So then we can also see the multiple image part. We have the mix up and cut mix. That is basically stitching different image together with a different strategy. A mix up, probably you switch the head of a cat into a cow, and a cut mix is like stitching two images together. So you provide more context information within one image. And mosaic is the data augmentation approach that YOLOv4 proposed, is basically stitching four images together. Later we will talk about that. And you can also using GAN as approach. Nowadays we all know that there is a different training strategy using the adversarial training. Later we will cover this part as well, because YOLOv4 is using the self-adversarial training in as a data augmentation techniques. So if we see the object occlusion part, from the image of object occlusion, you can have the zero mask or cutout, but for the feature map occlusion, it's a drop block. So basically, this diagram is just my personal brand map. I can always refer back to when I read some new techniques from the papers. I can always refer back to this diagram to understand which categories that falls into. Okay, so I won't cover all of them, so you can come back, always refer to this. And we're going to talk about BoF specials. BoF specials is basically the plugin modules that, or post-processing method that only increase in the inference cost by a small amount, but can significantly improve the accuracy. So what does that mean is these things put into your network, they have some computational burdens, but it's worth it. That is BoF specials. For example, we have the enlarged receptive field, the SBP, which is used in YOLOv4. And then nowadays, a lot of different attention model are used. Start from the channel-wise attention model, which is squeeze and excitations, or a spatial-wise attention model, which is spatial attention model, which is used in YOLOv4. Later, we'll also cover this part. And there is some feature integration like FBN or skip connection, and also post-processing with the different activation function selections and non-maximal suppression. So the YOLOv4 architecture selections criteria is trying to find an optimal balance among those different factors, but quite intuitively we can think about the input network resolution is the input image size. That is quite important because we know if you have a big input size, a big input image size, then you have more context information and you are able to detect a smaller object. But of course, when you have a bigger image size, means you need more memory bandwidth, you need more computational as well. So you need to find a balance among them, and that's quite important. And also for the additional blocks, we need something to increase in the receptive field, because we all know that while the receptive field size grows, we have more context information around the object and within the image as well. And we also need to find out what is the best method to aggregate information from the backbones of the different levels features to the detector. That is, we need to find a really good NAC architecture. So the final architecture that YOLOv4 is using, the backbone is using a CSPDarkNet53, and the NAC is using SPP and PANnet, and the head is still using YOLOv3. In the below table, you can see the different backbone model from CSP ResNex 50 to CSP Darknet 53 and compare with EfficientNet B3. You see they have the same input resolution image size, but they do have the different receptive field size. The EfficientNet B3 has the largest receptive field size, but the darknet is in between. But if you see the final frames per second, you can tell that the DarkNet53 is the fastest, and the efficient net B3 has the lowest B flops, but it is the slowest. So it also tells you some um, paradox that people think when you have a lower B flops, you can be faster. It's not always the case here. And also efficient net B3 has the smallest parameters here. Okay, so we're gonna compare the later we will show the result why they select him from ResNext 50, ResNext 50 and DarkNet 53. So we just talked about the selections between backbone architectures and the additional blocks, um, the neck structures, and also the head. Now we're gonna cover what is the selection of bag of freebies and bag of specials. So if you see this list here, there's the backbones and detector. And we're gonna cover today in this presentation the highlighted green one, because I already told you that I cannot cover everything. You see there's so many different techniques are applied in the YOLOv4 papers that gonna cost probably 2-3 hours to cover all of them. But we're gonna cover some of them. Okay. The first thing, the backbone, CSP, cross-stage partial connection. I think in late 2016, somebody proposed the DenseNet, and then the DenseNet is like put into the extreme from the ResNet, because we know the ResNet had this skip connection, um, but the DenseNet is like connecting everything together. And they claim that with doing this, you have a better gradient flow, since you know that every layer is interconnected to each other. The first layer is also connected to the output layer. So when you have the error signal backprop, you will also backprop directly to the input layer. So by doing that, you have a more efficient way of propagating the gradient flow to update your weights. But the CSP work, they found out that actually inside the DenseNet proposed method, they have a duplicate gradient flow information. So how they solve that is they proposed this cross-stage partial connections. And if we see the diagram in the right-hand side here, the base layer is separated into two parts. The one part will go into the original dense block, and then the other part will directly skip to the transition part. If you see the diagram in the lower part, that will show more detailed information that in a DenseNet, there is an input feature, and the input feature will have a convolutional layer output, and the conv output will concatenate with the input and output, and then follow this strategy, always have the input concat with the output sequentially. So what CSP do is it only take the partial in the channel wise, a partial of them into the dense block. And then also following the same strategy, concat with the input and output. But there is another part will skip all the way directly to the transition layers to connect it together. They claim that by doing that, it has more efficient way, because you don't have this duplicated gradient informations, and you can reduce a lot of computation as well. So we can see some result proposed show inside the CSP paper that by using the CSP integrate into the backbone, the ResNext can improve a lot of the performance in terms of the speed and accuracy. So that is why YOLOv4 is using the CSP as a backbone to the DarkNet53. They want to using this improved approach embedded into the darknet. Okay, so now we're going to talk about the YOLOv4 data augmentation approach. One thing I already mentioned before is the mosaic. This is stitching 4 images together, and the benefit of that is you have more context information within one image, which means that your batch normalization can have a 4x reduce, because before you're probably gonna collecting 33, 32 or 64 images as a mini batch, but now you can reduce like 4x. And the right hand side, you can see the self-adversarial training. We know that the network tend to have very bad performance if you have very minimum perturbations of the image. So if the network detect a cat within a minimum perturbation, the network can totally mess up to it is a traffic light. So what does YOLOv4 doing here with the self-adversarial training is to take the minimum perturbation but still using the original class label and bounding box to tell the network, hey, it's still a cat, there's no traffic light. And this is quite intuitive for human, but for a neural network, this is commonly a problem that suffer from adversarial attack. So they're trying to apply this self-adversarial training during the training time to create an adversarial attack already to have a more robust network in the end. So now we're going to talk about the YOLOv4 modification stuff. YOLOv4 modified 4 previous work, which is quite critical. The first is the spatial pyramid pool, and then the spatial attention model, path aggregation network, and cross-iteration batch normalization. Let's start with SPP. The original SPP is proposed, I think, in 2014 by Kai-Ming He. The original idea is try to have approach can have multi-scale input image training, because previously we are suffering from the fixed input image because of the fully connected layer. Because within the fully connected layer, you need to specify your input layers and output layers. And always before you have a lot of convolutional layers or max pool layers, you always need to flatten them. And this flattened part will be as the input of the fully connected layer, and that is the bottleneck of the network cannot change the input size. However, the SPP model proposed a different way of using the max pool bins to solve this problem. And if you see the diagram here, they're using a different size of the bins, which is all the max pool layers, put on top this feature map. And then you know that we have 16 of them, so I will come up with 16 result times across the channels 256. And this is 4 times 256, and this is only one max pool layer, so 256. So the final output of that is just 16 plus 4 plus 1 times 256. By changing this, you can always fulfill with the fixed size output representation. So that is the work that enable the multi-scale input size training within the original SPP. But the modified SPP is proposed of using the max pool of the input feature and with the straight one, so there's no reductions of the spatial wise information. So it keep the feature map size. Also, of course, the channel wise information is kept. 512 is still there. And then they concatenate 3 of them together within the original input together. By doing that, they claim it has a larger receptive field size, so it's beneficial for detector. Okay. And for the next model is the path aggregation network. The path aggregation network is trying to improve the work of the feature pyramid network. The feature pyramid network is in the left-hand side here. So before, the original feature pyramid network proposed the idea that we kind of need to also using the low-level features. So they're using the lateral connections with the element-wise additions to add in the information from the low-level layers. However, it doesn't show inside the FPN module is this journey gonna take 100 plus layers. So actually the low level features are losing along the way. So the pen work is trying to have a shortcut connection to make sure the low level features can connect to the high level within less 10 layers. So you can fully leverage the low level features information. And we all know that the low level features information contains with localization information which can help the detector to correctly localize the object. And the modification of the pen inside the YOLO is just instead of doing element-wise additions, it using the concatenations in element-wise in a different feature map. So the next model we're going to talk about the SAM, which is the spatial attention model. The spatial attention model is in the work of this convolutional block attention model. This is in 2019 work. But really the original one is the 2017. If you see the right bottom column corner here, we have the original SE. SE stands for squeeze and excitation model. So let's talk about first what is the squeeze and excitation model. That is a channel-wise attention model. So the channel-wise attention model, what does it do is if you have a feature maps as an input, what it does first is it first compress using the average pool along the spatial. So you only have the 1D output, but you keep the channel informations. This is called squeeze operation because you squeeze this height and width into one. And then you pass in through operation called excitation. So we can refer to the links here. We borrow the image from here. The excitation is exactly doing the multi-layer perceptions. That is the whole input of your layers go inside this excitation operation. What it does here is just squeeze with a compression ratio because we all know that a fully connected layer contribute to the multiple parameters. So we don't want this fully connected layers scattering around our architectures that will increase our computation. So we try to reduce them first, and then the final output will pass sigmoid functions to make sure the output is between 0 and 1. And the reason of using sigmoid function is not just simply because it compressed to 0 and 1, because you can also use in ReLU and do some mathematics operations to make sure they compress to 0 and 1. But the reason is they found out that in the original paper using sigmoid function tend to have a better performance. There's an application study for using different activation function, and the sigmoid is they chose. So we know that the output is just a 1D array length C along the channel, and then you have all the components with 0 and 1 there, and then you can multiply them together. You have this attention result here with the color encoded information. Okay, this is 2017's work. And in this 2019 work, the convolution block attention model, they argue why only using channel-wise attention model. I'm gonna use in both channel-wise and spatial-wise. So their work is composed with two parts, channel-wise and spatial-wise. And inside channel-wise, instead of only using the average pool as the original SE, they they do ablation study and say and it shows that using the max pool also generate a better result. So what I did is exactly the same, but just two operators, and then in the end, element-wise addition 2 to the 1, and then pass through a sigmoid functions. So you have the same here. So you do element-wise multiplication, so you have a channel attention aware input feature here. Then you're gonna pass inside another module called spatial attention model. And spatial attention model is in this block. So what it does is along the channel, there is a max pool and average pool operation. So you squeeze all the channel into only one channel and you concatenate these two operation output and followed by a convolution layer and then sigmoid functions. So then you multiply, you have the final output of that within the number 0 and 1, between 0 and 1 there, and then you do element-wise multiplication, so with the final output. And that is the original work for this paper. But inside YOLOv4 is here. It's only using the spatial attention model. And the reason for that is the channel-wise attention model of SE is not efficient on GPU. So most of the work using the SE is like doing TPU or CPU computation. So the YOLOv4 want to be really fast on GPU, single GPU, so they didn't use the channel-wise attention model. They only use the spatial attention model here, and then they modify the part of that. Instead of using a max pool and average pool along the channel, they do in a normal convolution, and then they do a point-wise element-wise multiplication, because they are not just a single feature map. It's everything here. So they take everything into block and do some multiplication here. That's their modification. So we are gonna talk about the CBN. In YOLOv4, it proposed another approach called here, this green box part. It's a cross mini batch normalization. Okay, then we're gonna trace back to the history of batch normalization in 2015. The work of batch normalization is usually within a mini batch size of 32 or 64. The reason for that is they need to tend to have a certain big enough numbers to have a representation of the entire data set. So you can sampling from the statistic point of view, you can sampling the mean and variance across, you can normalize with these values. However, nowadays we have the problem that the models tend to grow deeper and the input image size tend to be bigger. So within the not the high-end GPU, you don't have enough memory. You don't have enough memory capacity to store those models and also the batch size the image. So that caused a lot of different works to solve the problem how to deal with a small mini batch size. Let's say nowadays probably your GPU can only store 2 images, or you can only have a mini batch size of 2. And what is the problem of mini batch size of 2 is exactly you original idea of having mini batch is you collecting sufficient statistic data that can represent your entire data set. And now you only have a 2 image which cannot represent your entire data set, of course, then you tend to have a degraded performance. So the first, there's a different work, the group normalization, layer normalization, instance normalization. I think one of that, the best is the group normalization, also from Kai Ming He. But the problem of group normalization is it's too slow. So in 2019, there's another paper called cross-iteration batch normalization. They come up with the idea to collecting the means and variance across the different iteration. So you collecting the data across time domain. You find the means and variance across the time domain. So if you see the left-hand side image here, instead of batch normalization, if we see the current time iteration t, instead of batch normalization, you're only collecting the current fit-in batch. You are also collecting the data previously in the previous time frame. So you can collect it up to a certain age of your means and variance. And in this work, the most critical assumption is Taylor expansion, because you cannot simply add the means and variance from the previous iteration. The author observed that the weights across the different iteration is quite smooth. So if we know that respect to the weights, it's not as smooth, so we can use the Taylor expansions to derivative respect to the weights to collecting the information of the means and variance. Probably what I'm saying here is a little bit blurred. Please refer to the original paper of this cross-iteration batch normalization is quite interesting. But the bottom line information I'm trying to say is people trying to find a different way of collecting enough statistic information for the input for the training samples. Okay, so this work is across the time domain, and YOLOv4 is across mini batches. So they can have one mini batch can have two data. So I can have a 4 mini batches. I have 8 data. So I cross I cross mini batch here. I don't cross time domain. Okay. So now after introduce a lot of terminologies and the modification work, we're gonna see some result experiment. The dataset they are using is ImageNet for Classifier and the COCO 2017 for Detector. So the influence of the back of freebies and activations on Classifier is as shown here. So they do ablation study, and they first experiment on the CSP Next 50. They found it out with the cut mix, mosaic, and labeling smooth, and using the mesh, they tend to have a very good result. In the final, I boxes here, and they do exactly the same, but with the darknet, it shows a little bit great result compared to Next on the classifier work. So they have a conclusion that the CSP Next is outperform the CSP darknet on classifier task. So now we show the ablation study for the back of freebies on detectors, and the abbreviation I put it here so you can check the result. Basically, what they find out that using those different approach, which I didn't mention in this presentations, tend to have a better performance. So they're using that. As I say, it's a very engineering paper. Do a lot of ablation studies to understand the best combinations of the techniques. And then the influence of the back of Spatials on detector, as we mentioned, we want to have a pan with the shortcut connections from the low level layers to the high level features. We want to have SPP concatenate with the different output feature map to have a large receptive field. We want to have a SAM, which is the special attention model. So by combination of this on detector, it's the best result. But they are using still the Next for this because they are using the table from the CSP work. The CSP work only focus on the rest next. So they now compare the backbone on detector. They found out that the darknet is outperformed the rest next. This image is quite interesting. On the detector task, the rest next tend to perform a worse result while you add in the things before has better in the classifier result. So they do exactly the same on the classifier. You shows really good, but on the detector you degrade it. So they have the conclusion that the darknet is better or suitable for the detector task than the rest next. That's why they choose the darknet instead of the rest next. And then the influence of the mini batches on the detector. Here is very interesting things. They say they found out that the adding back of freebies and back of specials training strategies, the mini batch size almost no effect on detector performance. So I think this result is kind of debatable because if you remember, we are now using the cross mini batch normalization. So you tell me that now your mini batch size is 4 or 8, but you didn't tell me how many mini batches you collecting across different mini batches. So but anyway, the bottom line information is you have these techniques to collecting more samples across the mini batches, and also remember you have a data augmentation approach with using the mosaic approach during the training. So by multiply those effects, the generate output didn't seem that affected on the AP levels. So now we're gonna show this diagram shows the AP and AP50 with the different GPU architecture from Maxwell to Pascal to Volta. Yeah, the bottom line information is YOLOv4 is fast and also very precise, accurate. If you see the different architecture of the GPU, this is Maxwell. I would directly jump to Volta since that is currently they have a benchmark the best architecture. Although nowadays there is Ampere already, it would be much faster. I expected here. So the bottom line information is YOLOv4 is really fast and accuracy is quite high. And the highlighted with blue here is means it's over than 30 frames per second. And you can all refer those tables on the original paper. Yeah, that's all for the presentation.